I'm recording this video as a little walkthrough to help you maybe understand the reasons for doing the various steps in exercise 8, where we take on emerging hotspot analysis, and also maybe to, I don't know, to try to anticipate some of the errors and maybe to better understand just how long steps take. And this exercise, of course, it covered a new operation, really a new dimension in spatial statistics, that of time, that we're covering, that's kind of covered in ARC through this tool, emerging hotspot analysis. It's also been designed by me in this course as kind of an exercise in working with real data. Kind of by that, I mean data that might not be in a format that's perfectly designed to being an input for a given tool in ARC, and also just bigger. I mean, in kind of an application, you might want to even work with an area bigger than what we see here, kind of Bullock County, Alabama, and just kind of a few kilometers buffer outside of the county. Now I've just kind of gone through things in VLab this morning, and I noticed that I've gone a little bit out of order from what the exercise has, and that's fine. Raster to point, this conversion tool, really does have to be run first, converting each pixel value here in the input TIFF image to a point. The one I did out of place was project. This can be done right after. I mean, I could be done, I guess, before the conversion. I did it second. I think the exercise has you do it a little bit later. These two tabular operations, calculate time field, or calculate field. This just has us add the coefficient 2000 to the 2-digit grid code, and then to convert that 4-digit number into a date value. And as a date value, it's a valid input for our create space-time cube. And once we have that cube, we can run emerging hotspot analysis. So if you look at the times attached to these will give you a pretty good idea of how long it took me to run each one. So for the raster to point conversion, that's 17 minutes. I don't think it took quite so long. Well, I guess it did. I mean, maybe I had a few minutes in between. So on the order of 10 to 15 minutes. Same thing here for project to calculate field. Oh, here. I'm just looking at the catalog pane at right, but if we allow the pop-up to come, it does tell us the elapsed time. You can see there maybe 5 minutes, 44 seconds, so it was pretty quick. 11 minutes for project, 15 minutes about for calculate field. Converting time field was the long one. That took me an hour, 20 minutes. So it's something you just have run in the background. Create space-time cube. Can't quite see here, but it took, about 15, 20 minutes. And it took about 10 minutes. And once that was done, these emerging hotspot analysis that make use of the space-time cube just take a few minutes to run, and here I ran 2. Now when you get the warning here, it's not necessarily a problem. They just want to make sure you know what the distance interval is. And kind of those 2 runs, I didn't specify any specific distance, so it calculated one for me. Here, 663 meters, 3,746. And on the second one, the input space-time cube still has 663, but I manually input a neighborhood distance of 6 kilometers. So I'll try to walk through that process. Here, just have the TIFF band 1, so kind of shades of gray, kind of marking the year of forest loss. You can see they're patch by patch. They're not even pixel by pixel. But in order to create the space-time cube, we do need a point input. That's something that Esri's working on more lately, you are able to take direct raster data and use it to build a space-time cube. But the way that function works is to take kind of average values. So it's something, if we have a count like this, not perfectly well designed. And it's something you can do, but it would require just a little bit of math, a few more steps. And so this kind of a process is pretty representative of what still might be the way you would want to go about doing that. So the first step I had was to convert this raster to point. Click on this. Input raster, simply the TIFF. The field is called the value. So each grid cell in that raster has a value. And the output point features, I called them Bullock LY for loss year points. And if you look at all the the data, you can tell it's points, but I like to just put that in the title if I can to just keep things straight. So I'll simply add that back in. Projects, database, my project. We'll add in those points. And now these can take a long time to load. I think if you're working in ArcMap, you can just turn off the visual panel there, the kind of the data view, if you're working in Arc. Here in Pro, I'm just trying to click off the check mark there. Oh, you can see them kind of appear here with their white outline. It's just not useful to be able to see them. They're coming in. It'd take a few minutes to even load them. It's kind of strangely reminiscent, I think. If you go back to the era before I knew about GIS, before I was working, I don't know, 1990s, a lot of GIS applications didn't have a visual interface at all. It was just kind of command line based. So somewhat harder, maybe harder to interact with the data, harder to see what you're doing. Kind of maybe a brief window, about the time I was becoming aware of what GIS was, and kind of the decade of 2000 to 2010, when visual interfaces were kind of default part of every GIS application, and the volume of data would be such that you could actually view it and it wouldn't take forever to load. And now what we see, maybe over the last 10 years, are volumes of data that we can kind of get ourselves, get fairly easily about a number of different topics, are of such volume that they don't they're not amenable to easy visualization. At least not on every kind of setup. I think a lot of places where you're working, especially with maybe three-dimensional data, require machines with pretty advanced graphics cards. If we open the table for those points that are no longer visible, we'll see that they have these IDs, a marker of the shape geometry, and then a grid code. And this, it's 2 digits, but it marks the year of forest loss. So these 18 means forest loss in the year 2018. And the surface area covered by that grid cell had the kind of hallmark greenness. Basically, it was reflecting a lot of near-infrared light, absorbing a lot of visible range light. In every yearly observation up to 2017, and then, or up to 2018, and then in the 2019 data, that signature did not appear. Here is 7, so that's kind of the same timeline, but for the year 2007. And again, something that you see software applications improving in is the ability to take a 2-digit number, or 1-digit number here, and to pull out a year to it. I don't want to say that it's based off this specific application or this kind of area of working with deforestation data, but it works. Now, unfortunately, we have a single other step which requires a 4-digit year value, that YYYY in the tool documentation. And so the next step in the table is to get 18 to 2018, 7 to 2007. And what we do is add a field, call it year, have it be a long, that for long integer, that's fine. Oh, don't need another one. Simply save the edit. I'll add the field in. Close that fields view whenever it kicks back in. There we go. And now we see here year, type long, but all the values are none. So at this point we'd want to calculate field, grid code plus 2000. And now I would click run, and what we'd get is for every record that has an 18, 2018, for every 7, 2007, for every 15, 2015, and so on. What I'll do instead is I'll just add in the projected layer that I've done from these points. And you see for the project, what I ended up using for an output coordinate system was UTM zone 16N. And I also added that into the file name, UTM 16N. I think you'd actually get more precise spatial placement, like more locational accuracy, if you were to use the state plane system. But UTM zones are kind of applicable in the same way for every place on Earth. If you just Google UTM zone Alabama, you will get an answer. There are some areas that might lie very close to or on the border between UTM zones. Maybe for those, you can work with a modified coordinate system. But really, this kind of distinction isn't that important when we're working with just in an area the size of a county in Alabama. Now, the reason why we need to get to projected coordinate systems is because the tools that we'll use later on, the creation of the space-time cube in particular, require measuring distance. And location measured with a geometric coordinate system makes use of angular measurements. So we're talking about latitude and longitude. And if you remember, if you consult the globe, the distance between parallels of latitude are going to be approximately the same. We're measuring vertical distance anywhere on Earth. But longitude, measuring distance east to west, the meridians of longitude all converge at the poles. So what this means is that 1 degree of longitude translates to a slightly, or more than slightly, different length depending on how close you are to the poles, your latitude. Again, working in an area the size of Bullitt County, there's not that much difference between what a measure of longitude means at the north end of our study area and at the south, but there is going to be some difference. And with a tool like this, emerging hotspot analysis, using a standardized global product like these Hansen, Maryland deforestation data, I use this to measure deforestation in the Amazon basin, Indonesia, globally even, you could. And in that case, you would definitely need some sort of reliable standard measure of distance, so thus a projected coordinate system. So here I've added in the Bullock-Glossier points UTM, the projected. I've let it load. Now we'll go in to see the table. So there's the grid code, the 4-digit year, and year converted. Now this year converted was created through the convert time field. And this is the tool that took a long time to run. So input time field, your input table has to have this year, 4-digit year, so that it can be recognized with this YYYY input time format. Output time field, year underscore converted is just the default. It's fine to keep that. And then the output time type needs to be a date. And you can look at this and you can kind of imagine that this date, it's more characters than the year. You know, it marks January 1st with these dashes. It doesn't need to, but it does. Now the date time field, it's larger than kind of just a store of a number, but it stores this kind of time information in a standardized way, one that can be recognized by tools. And so that standardization is valuable. And kind of as the software engineers at Esri recognize it, it's worth the time to invest in order to ensure that the tool runs as designed. And indeed, this point file, 1,421,000 points, can be used as an input for creating Spacetime Cube. And the full name of that tool is Create Spacetime Cube by Aggregating Points. Your input features need to be the projected points. You're outputting a spacetime cube. It's going to be an NC file, netcdf, and so you're going to need to indicate a folder location to put it. So it's not something, I don't believe it's something that you can put in a geodatabase. A time field needs to be specified, and that needs to be a field that has the date format. So in our input, only year converted is recognized as a valid option for that. Template cube, this can take different time step intervals and distance intervals from an existing cube. We don't need that. I suppose we could have run optimized hotspot on the gains first and taken the geometry, but this is the way it's done. Time step interval, in general, we'll pick just as small as we can, reliably get. So here it's going to be 1 year. Keep the default end type, and then I asked just to leave the distance interval blank. You might want to pick a value. Maybe you'd run it blank first, get a value of 660, and say, okay, I want to do a nice round number, so I'll use 500 meters or so. Run that, and then about, 15 minutes later, that netcdf file will be created. And at that point, you can remove the points from the map project. They're no longer needed in there because the space-time cube is actually going to be the input for the emerging hotspot analysis. Now you can see when you look at the history in this project that I ran it twice. Right here, if you look at the details, it gives you the length for the distance interval, the time step interval. This is based on the grid, so this will be actually the same for each run that I did. Now what was different was the neighborhood distance, and what could have been different but wasn't was this time step interval. Summary of results, it gives you the kind of breakdown between all these different categories. I think no pattern is not really one here, kind of implied by this line. So they have 8 rows times 2 columns, 16 different possible outputs. What did I do here? I just used a longer neighborhood distance, 6 kilometers. So here's an output using a default calculation of the neighborhood distance, about 3.7 kilometers. And you see kind of a wide variety of modifiers in the legend here used to describe changes in space. So we see kind of red and tan shaded symbols for hot spots, bluish for cold spots, and then white for no discernible pattern. Things with dots, dotted texture marks sporadic or oscillating. And now you need to kind of consult the table that Esri's devised for this to know that sporadic and oscillating hot spot or cold spot mean that it is observed to be a hot or cold spot in the latest time step. So an area, a neighborhood represented by this grid cell in kind of the last 3 years of data, and areas within 3.7 kilometers. But then in past time steps, so not the latest 3 years of data, but the first 3 years, or I don't know, some sort of 3-year span in the middle of the 19, 20 years that we're looking at. That location and the neighborhood around it were not a hot spot at all. Or in fact, for oscillating, it could have been a cold spot at some time in the past. Now, that's a lot of categories. It's 16 plus no pattern detected, so we're looking at 17 different categories. I mean, they're not even trying to use color to distinguish these. There's kind of basic color distinction, and then a lot of different textures, and even different types of texture. It's kind of messy. And you should know that it's not based in any kind of, underlying inherent property in the data or the analysis. This is a scheme that has a logic to it based on change through time that was kind of devised by people, implemented in ArcGIS. So it's kind of a proposed way of doing things that they're putting forward as a good way to do it. It may or may not be good. One of the very clear drawbacks is difficult in interpretability. So just hard to tell what's going on overall. So one way to get a better sense of that is to run the tool again with slightly varying parameters. So I did it again with 6 kilometers as the neighborhood distance. You might think maybe it makes sense to just do twice, but I didn't want to get too big, just given the scale of the input data that we have. If we turn on that layer, you'll see that the same categories are used, and overall, I guess the pattern is similar. So we still have kind of hot spots in this southern area, cold spots in the northwest, but the texture of the outputs is going to be a little bit distinct. So here's the output using a 6 kilometer neighborhood distance. So as I said, still hot spots in the south center, cold spots in the northwest and the northeast. You can kind of flip back and forth in the video. I think that's going to be quicker than using Arc. It kind of takes a little bit of time every time I click on and off. But you can start to appreciate how increasing the neighborhood distance decreases the kind of fine scale spatial variability in hot and cold spot. So we're still using grid cells to represent the hot spots. But each grid cell is representing not just the count within its little area of that location, but the count in the neighborhood around it. And by toggling, really by increasing the neighborhood distance, we're increasing the overlap between the neighborhood of this grid cell and the neighborhood represented by the grid cell to its left and to its right and above it and below it. So what that does is kind of smooths out the patterns. It doesn't give you entirely new patterns on the kind of the regional scale. We still see a lot of hot spots where we saw a lot of hot spot before, a lot of cold spot in the northwest, but there aren't as many of the little patches We still have them, and they could be a little bit different, but in general, big picture, a lot of the message is the same. Iterating the tool like this, running it over with slight variations to different parameters, and then seeing the resulting changes that you get in outputs can give you a sense of how robust your outputs really are. So of course, we're using data from year 2000 to 2020 to calculate this, but we're kind of what's implied in that is that the findings will be at least somewhat interesting to what might happen in 2021 and 2022 and so on. And so for the kind of extrapolations, so trying to make predictions or understand phenomena outside the range covered by our input data, kind of a good sense of that robustness is really in order to set how much confidence you can have in those predictions.